Let's assume this is a mechanical clock from 1972 and you let it run untouched until today. It would be exactly 27 seconds ahead of your smartphone. But if you turn on the navigation system of your unpatched car from 1980, its calendar will be trapped 39 years, 4 months in the past. It's the same bizarre error everywhere, be it New York, London, Cairo, Tokyo, or Mumbai. And they all expose one massive, terrifying secret. Our time is broken. When we think of great scientific mysteries, we imagine black holes or the quantum world. But the greatest mystery is something you have lived with every second of your life: time itself. It's the invisible flaw behind the Y2K panic, and today our computers are racing towards another countdown, one that experts warn could affect the GPS, banking, and the digital infrastructure that keeps modern civilization running. To understand why, you have to realize that humanity has been quietly editing time for decades, and the weirdest part, you never noticed. While your watch looked perfectly normal, the digital world behind it was constantly being patched, hacked, and forcefully synchronized to something far less stable than you might think: the wobbling rotations of the Earth. See, there isn't just one kind of time. And to understand this invisible war being fought on your phone screen right now, we have to go back. For thousands of years, measuring time was easy. We simply watched the Earth. One full rotation meant one day. It worked until we learned something surprising. Earth isn't a perfect clock. Its rotation isn't constant. The moon's gravity, earthquakes, shifting oceans, and the movements inside Earth's core all make our planet spin ever so slightly faster or slower. That wasn't a problem for ancient civilizations, but by the 1950s, science had become so advanced that time measurement had to be precise to the very nanosecond. Time based on Earth's rotation was no longer accurate enough. So scientists stopped relying on the sky and started looking at the atom. Instead of measuring time by Earth's rotation, scientists turned to an isotope called cesium-133. From it, they built a new time scale called atomic time. Contrary to popular belief, scientists don't actually watch cesium atoms vibrating. That's impossible. Instead, they fire the microwaves at them, almost like tuning a radio. If the frequency is wrong, the atoms ignore it. But the instant the frequency is exactly right, the atoms respond. So the clock keeps adjusting the microwaves until the atom says, "Yes, that's the one, buddy." That frequency is so perfectly constant that humanity decided to build the definition of time around it. That's exactly 9,192,631,770 oscillations of cesium-133 atom defines exactly 1 second. And cesium-133 isn't just another atom. It is the atom humanity chose to define reality. Problem solved. Or so we thought. Because atomic clock kept perfect time, while Earth didn't. Slowly, the two drifted apart. If we followed atomic time alone, noon would gradually stop matching the position of the sun. So in 1972, the world created Coordinated Universal Time, or we famously known as UTC. UTC is a compromise. It follows the incredible precision of the atomic clocks. But every so often, it pauses for a leap second to stay synchronized with the Earth's imperfect rotation. In other words, we didn't replace Earth time. We didn't replace atomic time. We invented a third kind of time that constantly negotiates between these two. Our global standard, UTC, is built on the perfection of atomic clock, but it is also forced to bend to the will of Earth's uneven spins. That messy collision is exactly why something called leap seconds exist. And it's about to trigger a digital reckoning. Here is a story of how we broke time and how it is about to break us. To understand the chaos heading our way, we have to look at three seemingly minor engineering decisions from human history. The three moments where we tried to bend time to fit our technology, and we built a digital time bomb. The first is the 1972 compromise, the birth of leap second. In 1972, humanity officially introduced the leap second because atomic clock and the planetary time naturally drift apart. Our solution was a new standard called Coordinated Universal Time, or UTC, as we discussed earlier. UTC is the everyday civil time. To make UTC work, we forced the digital world to periodically freeze for 1 second so the Earth could catch up to our atomic clocks. If you look at the chart of this negotiations, you could see the problem right away. When the system started in 1972, atomic time was already 10 seconds ahead of the Earth. Since then, we had to inject 27 more leap seconds into our civil time just to keep things aligned. If you do the math, adding those 27 new leap seconds to the original 10-second head start is exactly where a magical 37-second gap comes from today. In the beginning, the Earth was slowing down fast. Throughout the 70s, 80s, and 90s, scientists were forced to alter civil time almost every single year, including back-to-back edits in 1972, 73, and 74. But then, the planet did something weird. It started speeding up. In the entire 21st century, UTC has needed only 6 leap seconds, with the very last one added on December 31st, 2016. And we haven't added a single one since. That unpredictability is exactly what makes leap seconds such a nightmare. They kept our clocks aligned with the sun, but they also introduced a serious problem for modern computing. Computers expect time to move forward in a perfectly steady rhythm. A minute is supposed to be exactly 60 seconds. But every time we occasionally stretched a minute to 61 seconds by adding a leap second, software can become confused, programs crash and servers glitch, and the systems that depends on precise timing can fail. And that's the strange compromise we call a leap second. And later in the video, you will see how we dealt with it. In 1980, the United States military launched the Global Positioning System, short for GPS. To tell a car exactly where it's on a highway, satellites have to calculate the travel time of a radio signal down to the nanosecond. To do so, the car and the satellites must be locked to the exact same clock. But engineers ran into a problem. Tracking civil time or UTC with all its chaotic, unpredictable leap seconds was too risky for military navigation. If a leap second suddenly paused a satellite clock while a fast-moving car was calculating its position, the navigation system would fail. So engineers bypassed civil time entirely, but they couldn't just use the existing International Atomic Time, short for TAI, because by 1980, the atomic time was already 19 seconds ahead of the real-world calendar civilians actually used. Military operations needed to line up with everyday dates, so they compromised and they created a brand new atomic time called GPS time. They synchronized its starting line to match civilian time on Jan 6, 1980, but ordered it to tick continuously from that moment on, completely ignoring all future leap seconds. And this created 2 separate atomic time operating in parallel. But to track the calendar date on this new timeline without wasting expensive satellite computer memory, they made a massive mistake. They chose a tiny 10-bit digital counter to track weeks. The problem, a 10-bit counter can only count up to 1,023 weeks, which is roughly 19.7 years. The exact moment it hits the week 1024, the counter silently resets to 0, because unpatched navigation systems don't know a rollover happened, and they see week 0 and assume they traveled decades in the past. Because we are living in the 3rd GPS cycle, an unpatched dashboard clock today will loop back 2 full cycles, instantly trapping your car calendar exactly 39.4 years in the past. Y2K was a proof of what happens when software makes lazy assumptions about time. To save precious storage space in the early days of computing, engineers dropped the 19 from years, leaving just 2 digits. When the year 2000 arrived, computers read it 00, not as a new millennium, but as the regression to 1900. It cost billions of dollars to patch, yet we treated it as a one-time glitch instead of a warning sign. For decades, humanity didn't fix these structural flaws. We just slapped digital band-aids onto them. To deal with Y2K issues, armies of programmers pulled all-nighters, rewriting those ancient codes, expanding the 2-digit year field back to 4. It was a brutal multi-billion-dollar race against the clock, but it worked. To deal with the GPS rollover, engineers didn't fix the unpatched cars already on the road. They just forced a newer receiver to rely on a clever software trick. Modern GPS softwares use an internal anchor date, like the year the chip was manufactured, to guess which 20-year window it's currently in. Furthermore, modernized satellites now uses a new 13-bit counter that won't roll over for the next 157 years. And the leap second? Tech giants like Google and Meta got so sick of the servers crashing every time a leap second was added, they invented something called a leap smearing. Instead of injecting an abrupt, chaotic 61st second, they spread that extra second into thousands of microscopic milliseconds, quietly slowing down the computer clocks over the entire day. But smearing time was never a real solution. It was just a bandage on a fracturing foundation. For decades, every leap second has been positive because Earth's rotation was gradually slowing, forcing us to occasionally add an extra second to UTC. But in recent years, Earth has unexpectedly begun spinning slightly faster on average. For the first time in history, scientists have had to prepare for something that has never happened before: a negative leap second. That means deleting a second instead of adding one. That may sound like a tiny change, but many computer systems were only ever designed to handle an extra second, not a missing one. The prospect of introducing the world's first negative leap second raised serious concerns throughout the computing and navigation industries. As our infrastructure grew more complex, international metrologists reached a conclusion: we couldn't keep manually editing civil time forever. That's why the global scientific community voted to phase out leap second by or before 2035. For the first time in human history, we will allow a civil clock to slowly drift away from the Earth's rotation, choosing digital stability over astronomical perfection, because a much larger threat is lurking just past the deadline. The year 2038, the epochalypse. Right now, the entire digital world is racing towards a hard math ceiling, and even known to computer scientists as the epochalypse or the year 2038 problem. To understand why this breaks software, you have to realize that the time you see on your app screen is a lie. Most computers don't understand month or year. The background code of almost every computer, server, and the phone on Earth relies on something called Unix Time. Unix Time behaves like an unblinking stopwatch, counting time continuously in a raw second from a fixed point in human history known as the epoch. That is midnight of January 1st, 1970. But here is the ultimate catch: Unix Time completely ignores leap seconds. According to the official PASIC standard, Unix Time operates on a strict math shortcut. It assumes every single day has exactly 86,400 seconds, with no exceptions. Because Earth has added 27 extra seconds since 1972, true Earth time has completely outpaced the computer system, and your phone is actively pretending those 27 seconds never happened. This means that right now, in the deep background of almost every application, database, and server, Unix time is exactly 27 seconds behind true UTC time. Your phone screen and computer clock only looks correct to you because background internet time servers are constantly intercepting the feed, forcing a messy visual translation into your local time zone. But deep inside the code, you cannot directly convert a Unix timestamp into a human-readable UTC date without manually programming a lookup table to account for that exact number of accumulated leap seconds since 1970. To make matters worse, when the system was built, engineers chose to store the running count of seconds as a single 32-bit integer. In simple terms, a 32-bit data container can only hold a maximum value of 2,147,483,647. And that brings us to Tuesday, Jan 19th, 2038 at exactly 3 hours, 14 minutes and 7 seconds UTC. In that precise second, the Unix counter will hit its hard mathematical ceiling. It will completely run out of memory bits because it cannot count any higher. The numbers will instantly flip a negative switch and roll back to Friday, December 13th, 1901. Unpatched systems worldwide will instantly believe they have traveled 136 years into the past, threatening legacy banking networks, automated power grids, and embedded infrastructure. Suddenly, the automated banking system will process transactions from a century ago. Critical infrastructure, unpatched routers, embedded medical equipments, and older industrial systems will suddenly think they are operating in the era of steam engines, causing them to instantly crash or reject security certificates. Unlike the Y2K issue, this wasn't just a layout flaw in how we wrote dates. The 2038 bug is a hardware-level math limitation embedded in the millions of active devices worldwide. If you don't swap out or upgrade every 32-bit timer to a modern 64-bit systems before the Tuesday morning, the digital illusion of time will fracture, and the infrastructure based on 32-bit will stop ticking. Your laptop or your PC and the phone you're likely watching this on are completely safe. Modern consumer electronics have already upgraded to the 64-bit architecture. While a 32-bit systems run out of room in just a few decades, a 64-bit system expands the math ceiling to a mind-boggling scale. It can count up to 9 quintillion seconds. That means your modern devices won't experience an epoch overflow for another 292 billion years, long after our own sun burns out. Software engineers have known about this for a very long time. The Linux kernel has already introduced updates to allow systems to process 64-bit time tracking. Programmers worldwide are systematically locating these ancient systems to update or replace them well before 2038 arrives. The real battle in 2038 isn't against our daily tech. It's a hidden war to patch the ancient, invisible infrastructure running silently in the background. The next time you glance at your phone screen, remember that simple number is not a fundamental law of the universe. We spend our lives chasing time, trying to save it, spend it, or manage it. But as we have seen, the flow, the measure of passage of time isn't something we can truly agree on. It's a continuously patched negotiation between a massive rock spinning through deep space, the atoms, and the code of the human engineering. And thank you so much for spending few of your 84,400 seconds with me today. If you haven't already, please take a few more seconds to subscribe and check out the echo verses at the end of this video. And thanks again for watching. The atom beats a perfect drum, while Earth refuses that rhythm. Between the two, we built a bridge to keep our borrowed seconds stitched. A billion clocks begin to dream of perfect time without a seam, to live inside a synchronized dream. But when the hourglass runs out, the clock won't know us anymore. We believed that by measuring time, we could master it. Yet, every clock we built revealed another mystery. Reality was never willing to fit inside our equations. Each generation believes it has answered the final question. Yet, every generation discovers a deeper question waiting beyond it. Perhaps this isn't humanity's greatest weakness. Perhaps it is both our greatest privilege and our greatest curse to stand before an infinite universe, knowing we will never reach the end of its questions, nor solve the equations. Earth kept dancing, sometimes a little slower, sometimes a little faster, not to the tune of time, but to its own. Maybe there is something to learn from that. Not everything beautiful moves with perfect precision, and maybe wisdom isn't forcing reality to match our clocks. Maybe it's learning to move with reality instead. So be a little more like Earth, keep dancing, create your own tunes, live your life, and find your own pursuit of happiness, because you're unique, my friend. Keep questioning, stay curious, pass on the mantle, but never leave the path of your pursuit. Be it for passion, be it for happiness, be it for your goals. Your pursuit is uniquely yours. Stay blessed.
A random shout out to our community members to show my appreciation for your support. Thank you.